So, good morning, everyone. That be here and contribute to that wonderful Users Day. I have the pleasure to be the first in the I/O section, so I will also give an introduction into everything. And thus, my title of the talk is what are actually ad hoc storage systems, which are kind of the core in the my project. And in that sense, I give an example on the gekkoFS file system, which is one of the main file systems that we're using at Admire. So first off, to give an initial introduction, how do we generally today on a cluster use the parallel file system, right? The parallel file system is Lustre or gekkoFS, and the way that it usually works is that the user asks for a job with a batch script that is representing the application that runs. It could be, for example, an API job. And then the application is just communicating directly with the parallel file system, right? You're using Lustre just as any other local file system. You assume that it works exactly the same way, and this is what we call POSIX semantics, or strong POSIX consistency. And however, you are sharing this file system with everyone, right? So you also have interference. If one application is behaving badly, you will also feel it on the same end. So, and this is here 50 meters away on the Mare Nostrum 4 supercomputer, where we ran some tests. And what you see here is basically every dot on that slide is one experiment. It's just a benchmark, basically an IO benchmark. And this was executed, I think, for a week at different times of the day. And what you see here is that depending on when you execute it, you get a completely different performance. And this is orders of magnitude different, right? And sometimes you will see that even you have only like 100 megabytes per second for one node, right? Which is of course nothing if you think about what a parallel file system is representing, that it should be scaling. So the more applications are running, the more interference you have. So what can we do about it? So nowadays on many clusters, we have this node local storage installed. This is just every compute node on many clusters has node local storage installed. This could be an SSD, this could be SATA SSD, for example, an NVMe SSD, for example. And here at Mare Nostrum, we have a peak IO bandwidth from the over 200 gigabytes of reads per second. But of course, if you distribute it over all the nodes, divided over all the nodes that are available, it's just down to 60 megabytes per second. And if you have one node local storage SSD per node, you would have theoretically higher performance. So the idea is, because these node local storage are just local storage, right? And if you need a distribute namespace, you can actually not use it, is to include that in the HPC storage hierarchy, right? We have an additional IO layer here. And then the idea is to just deploy a file system within your job that is started, and it will just take all of these SSD and all your nodes in your job, put them together into one big SSD, basically, where you get the performance of all SSD and also the capacity of all SSDs, right? And then we can offer file system features that are not the same as a parallel file system would, that are fitting to the HFC applications. But overall, you can think of it, improve data locality and do the work where actually the data lives and not talk to someone else. So to give an analogy here, we have these dogs that are running around, each with their bucket of food. And this should represent the applications. So the data manipulations here rely on the parallel file system, and you have uncoordinated application IO to and from the parallel file system. We've just seen this in the figure. And we have this huge variability. And then at the same time, we have this node local storage down here that is just sitting there and does nothing, right? Because the application needs a parallel file system. So it's uncoordinated, random, apparently IO. So I want to move to this, where we have a much more coordinated IO here, in which the data manipulations rely on node local storage, and then the data that's written to this node local storage is then moved in and out to the parallel file system, right? In the beginning, the input data would be moved in, and the output data would be moved out to the parallel file system at the end of the job, and this is what we call staging, right? So then the application here is working on this green part, which is representing the ad hoc storage system. So, and at that point, because when we write out it's also sequential IO, we have also much better behavior from the parallel file system, which back in the day, this is what they're made for, sequential large IO requests. Right, so how do ad hoc storage systems work from the user's perspective? So this is an extended part now, where the ad hoc storage system are in the middle. And at that point, the application is doing only with the ad hoc storage system. Then there's a stage in, stage out part to the remote storage system, which is represented in the parallel file system. The problem here is that the user still needs to do all of this themselves, right? They need to start the ad hoc storage system on the nodes, they need to move the data in and out and so on and so forth. And this is, of course, not exactly transparent. This is what we want to change with that model. So at that point, I want to introduce gekkoFS, which is a burst buffer ad hoc file system that we are developing now for several years at the Johannes Gutenberg University in Mainz. And it was supposed to target and challenges where parallel file systems would not work very well, and specifically target these node local storage. And so the goals for these file systems were, first off, scalability. You probably know for a parallel file system like Lustre or gekkoFS, if you add more hard disks to the backend, right, it scales typically well with sequential data. But for random IO, especially with hard disks in the backend or for metadata workloads with many files, then they start really, break off very fast. So the idea of such a file system is, of course, if it doesn't scale, it makes no sense. So first goal is scalability. If you have twice the nodes, you have twice the performance capacity. This is the idea. At the same time, we relax POSIX semantics. This is a little bit more complicated topic. I won't go into it, but at the end of the day, it is made for HPC application and not for users, and thus we support this specific workloads. The next part is user space. This basically means that if you're a user, you can just use it as any other application, basically, right? So the administrator of the cluster won't even know that you're using it. You just see that it's better IO. And this allows us from the developer perspective also to break out of some restriction that we would have if we would go through the Linux kernel. The third point is fast deployment. Of course, you cannot spend several minutes to start up such a file system on the nodes, right? Compute time is precious, you can start waiting. So also the load is less than 1 minute for deployment, and for gekkoFS, we can start up on around 500 nodes in a couple of seconds, right? Very fast. And lastly, of course, hardware independence. We should be able to use everything that is available on the node local storage side. We should be able to use SSDs, NVMe SSDs, memory as well, and also support the native network protocols like FreeBand or OmniPass that are available on the supercomputers nowadays. Now the architecture, this is of course very technical, but just to give you an idea how that works, in general you have servers that you start on every node, and then you preload your application with an interposition library. This is what we call LD preload. So you just feed in your library that represents a file system client as an LD preload environment variable, and then you start the application. In our case, it's a little bit more complicated because we only intercept system calls, and we're not intercepting every single SCDIO function that comes from the application. So for us, we are much more compatible in that sense as well. Of course, we don't want to reinvent the wheel, so we are implemented our architecture based on existing well-proven designs, which is one is Mercury, which is our RPC framework. We're using RocksDB as our key value storage on the nodes where we store metadata. And then also syscall interceptor, this is how we intercept syscalls. So to kind of wrap up here, what is gekkoFS not? It's not supposed to be a Lustre or gekkoFS, right? It's not supposed to be a long-term general purpose parallel file system. It is supposed to be ephemeral, and that means that the lifetime is linked to an application or workflow, right? It could be a single application, but it could also be multiple applications where you have different phases that are spread over multiple jobs. This could also be a use case for it, but in general, it's ephemeral. Then it is not multi-user, so it's not supposed to be used by many jobs at the same time. It is possible, but since we do not really have these normal user privileges that you have in Lustre with permission and such, you can just access the data when you have actually access to the file system. This is another optimization to improve performance here. Then gekkoFS is not POSIX, and again, that just means we are more compatible with C application as just with users. If you want an example, for instance, even though we support operations like listing a directory, for example, or renaming a file, it is not optimized because applications are usually not doing that. This is something that users do afterwards. And gekkoFS can also offer specialized APIs. And that means you can also link gekkoFS against the client of gekkoFS without preloading it. This is also possible. So what is it then? It is supposed to be a distributed file system for a single application that aggregates the node local storage for performance and capacity. And then you have a shared namespace between the nodes that every node can see. So if node A writes something, node B can see it immediately. Again, it's intended to tune for a specific application. We have a lot of configurable things in the file system that you don't need to mess with, but we can do it to further optimize. This goes to metadata management and also how we distribute data, for example. Lastly, because we are running in user space and it's not kernel, it's very easy to use. You can just install it yourself and just use it. Right? There's no one stopping you. We have normal permissions, administrators who won't care, because to them, again, gekkoFS is just another application. And lastly, it's highly scalable. I will show that later, just as some form of evaluation, what you can expect as a performance. So this was evaluated nowadays we have it evaluated on many clusters, but this is an example from the Morgan supercomputer at the Johannes Gutenberg University in Mainz in Germany. And this is the MD test benchmark that you maybe also know from the IO 500 benchmark series. But in that case, what is happening, we're just creating a bunch of 0-byte files, 100,000 files per process, and weekly scale that, right? So the workload doubles with doubling nodes as well. So that means at around 500 nodes, we have over 800 million files in the file system, and we're close to 50 million creates per second, right? To put this into perspective, if we compare that with Lustre here, which is working on a typically on one or at least a couple metadata servers, you see that it stagnates, right? So we have here the operation per second on the y-axis, and while you get some performance improvement in the beginning for Lustre, it just stagnates, right? And you are in the ballpark around 30,000, 40,000 creates per second. And the same is true for Stat. There are two cases here for Lustre. One is if every process is working in a single directory. This is probably, as you heard from your administrator, not recommended, and people should typically use a directory per process. This is how Lustre works internally, and you see it, especially in the end, it doesn't really make a difference, but in the beginning, if you have little nodes available, you have better metadata performance here. But for gekkoFS, we have linear scaling. When you add the nodes, you also have the performance here. Now, the same is true for performance. It doesn't really matter if it's random or sequential or shared or file per process, you always see kind of the same performance, and this is the way how we do it in the backend. Now, what you see here is one example of sequential throughput, write and read throughput in different exercises, so from 8K to 64 megabytes per second. And you also see the SSD peak performance. This basically means, well, if you have 500 nodes and you put all SSDs together, this is your performance that you couldn't get at a maximum. And here we are, for 512 nodes, and big IO size is very close to it. Of course, there is a network tax where you cannot reach that local performance. But if you go down with your IO request sizes, of course, it gets stored because then your latency bottleneck basically. Right, so you have more headroom for the SSDs. We can also compare this with Lustre, but to be honest, this really depends on the installation, right? If you have a really big Lustre, the break-even point for ad hoc storage system makes sense. A little bit different if you have a smaller Lustre installation. But in generally, also these parallel systems scale well if they are completely undisturbed and you have them to yourself, which is usually the case. So if we go back to the figure that I showed in the beginning for the variability, you're using your own file system, and therefore there's no interference, right? So if you add nodes, you can basically extract linear scaling. This is what you see here as well. And therefore, if you use Learn to start a job, you also have a much better idea on how much time you should actually allocate for your job, right? Because you don't have this variability and you don't need to account for it. All right, again, so this is before Admire. The users manage that themselves. So how does it look in Admire? The idea in Admire to make this all transparent. And now we have additional components here, which is called stored and cargo. And these are just fancy names, but in general, stored means managing ad hoc storage systems. So they start and stop it for you. They can also control through, this is also part of Admire, that we have malleability in the sense that we can expand the number of nodes, right? We can add nodes during runtime of the ad hoc storage system, and then also improve performance while it's running. And cargo is an extension of stored. And as the name suggests, with cargo, you basically take data and move it around. And the idea is here that stored is also managing the staging in and staging out between the ad hoc storage system and the remote storage system. So the user does not have to do that anymore. The only thing that the user has to do is they basically has to ask, like usual, for their job. And they also need to tell us, well, I want to actually use an ad hoc storage system, and this is my input data, and this is where my output data should go. And everything else is then managed by this new stored and cargo component that is added in Admire. Now, I don't go further because Admire is, of course, a lot bigger than that, but the link to the rest of the Admire infrastructure that you see over the course of the day is then connected to stored. Right? So this stored is also an abstraction layer to the other storage systems. We are only controlled by that application. So there are incoming requests here to stored as well that could say expand this ad hoc storage system or similar, and so on and so forth. So just to give an idea how that works, how you would start a ad hoc storage system like that if you're not an Admire, because gekkoFS is of course also standalone. So you can just clone the Git repository, or you can just use Spuck. Right? Spuck is this user space package management for HPC. There's also gekkoFS there available. Although at the moment it is only in our Git repository, you first need to add it to your Spark namespace. But then once it is installed, you can just start the service with the gekkoFS application. This is a script that is in our project, where there's a config, which you can set a few configurations here, where your binaries and so on and so forth, and then you say start, and it starts on all nodes. You could also do this manually. If you just use it on one node, you use the gekkoFS daemon, which is what the gekkoFS script is starting. And I showed this because to give you more an idea how that works, because with gekkoFS you need two things. First, you need to say where the data should go, and this is the node local storage. And then you should say how the application should actually access that namespace, right? Because we are presenting a virtual mount point because we are not a kernel file system. So this is with this -m parameter. And then you have -h, which is a host file. And this is where the servers are registering themselves. So one host file is representing a file system instance. And then finally, for the clients, there's also two things that you need to do. The first part is abstracted away in Admire. So you need to set an environment variable that shows to the file system instance so that the clients actually know where to talk to. And the second part is then just preloading your environment, right? And this is done with these LD preloads here. You set the libgekkoFS intercept shared library, and then you just use the application. If you use MBI, you would use a -x parameter. If you use srun, you can use it like that. And all of this is abstracted away in Admire. So first, I'll show you some demo, how that looks with NEC 5000. So what you see here is two things. You see on the left, gekkoFS with NEC 5000. NEC 5000 is a CFD application, which is about synchronous application. So every number of steps that you define, you write out some data from checkpoints and statistics and so on. And you have on the right side NEC 5000 Lustre. And here you just see the workflow, how that works. So for Lustre, you just start your script. it goes directly to the compute nodes, and then the application is going to Lustre. This is how we're using it nowadays. If you use it with gekkoFS, then you first need to start the server, of course. But then again, you use it the same way, but instead it's not going to Lustre, but to gekkoFS. You need to stage load later. So let's see how that works. So we will compare here Lustre and gekkoFS. We'll run them at the same time and see the time. So here an example how NEC 5000 is run. It's as you would expect. You have an MPI application, you have a host file for your MPI, and you have your binary that you're running. And this is it for running NEC 5000, and we do this on 32 nodes, 16 processes each. So this is very straightforward. And then, of course, you have also some input. This is here, so we have a Lustre Scratch file system here with the input that is consumed and configured for the NEC 5000 installation here. And these are just the files that are needed. So these would need to be moved to gekkoFS first. But Lustre, of course, we can just carry there. On the top left, we are now starting gekkoFS, and this is the gekkoFS script or command that I showed you just with the gekkoFS config. And you just say start. In this case, you have more parameters. Run it in the foreground in 100 nodes. This is how the gekkoFS config looks like. Most can be state default, but the first two, for example, the daemon binary and the preload library, depends on the installation where you install it. So this needs to be modified. But in the future, this will also be more transparent, and you don't need to do anything. So we are on the top right logged in with one node, where we look at that host file where the file system is registered, and now we start it with this gekkoFS command on 100 nodes. And it's done. It took only 2 seconds. And you see on the right, they're already registered. And now you can basically use your application. We start here the HTOP application in one node, so you can actually see that something is doing something, right? And the bottom left, gekkoFS client is an alias with early preload to the library. So you can also do that, make it a little bit more transparent. Of course, the file system is currently empty, so we first need to copy the input. And this is what is done here. In line 6, you see that the input that is used also by Lustre is first copied into gekkoFS. And again, this is done in my by cargo. And we see this later as well. And then the 9th line is very much the same. You just need 2 environment variables, and then you can use it. And now we start it. And let it run. So input is already copied. It's not that much in this case. And it's running. And now it's Lustre as well. And of course, we accelerate a little bit because we want to sit here a couple of minutes. So gekkoFS is finished, and you see on the right side here that Lustre is stopping every now and again. So it's not able to consistently write out on the performance. And what you see here in this case, gekkoFS took 1.5 minutes, and yeah, Lustre took twice as long. It is important to note that this, of course, is dependent on how your application is doing I/O and how it is configured, right? So if you have a computation, an application that is only doing compute, then obviously there's not much I/O on the network storage system cannot help you, but the more I/O is happening, then network storage system come ahead. So how's that looking then in Admire? So we have new Slurm commands to let you not. So you saw how we can manually start gekkoFS, but of course Admire should do that for you. And we have new Slurm commands here, which is, for example, the ad hoc context where you can say, well, I want to have it shared, so the compute node should share the file system node, or we have dedicated. This is the bottom right here. Where basically your file system is on separate node as your application. If this is something that's useful, and then you can also set the number of nodes that you want in this case. Then in addition, regarding data transfer, we also have some new Slurm commands here. And you specify your input and output by origin to target or both. And here we have an example down here for S-batch. So we have the input that is going, for example, from Lustre, in this case, to gekkoFS to some tier. And the same with output, you can also define both. So, but this is supposed to be all transparent. So now we see how stored interact with the ad hoc storage, and we don't see the data movement here. So, but we see that the ad hoc storage system are started with stored. With this management component that we have in Admire. Yeah, and then that is actually working. So we're doing the same thing with HTOP here to see that something is happening on the bottom right. And then in this case, to show that it works, we're using the DF application, which is of course giving you the space that is available. Again, you see the gekkoFS config, you've already seen this. But for DF, what you would see if you just individually have two nodes and you started on the local SSDs, then you have, 2 times the space, and it's not bound together. And when you start gekkoFS, it is bound together. So here we show some configurations that is this is transparent, but this is something also that we need to set so that scores can also talk to our remaining components in Admire that you see in the later talks. So now we're running just showing you the srun and the new ad hoc new Slurm commands here that are provided. Like the new Slurm language with ad hoc nodes, you have wall time, context, and context ID as well. Now we start Scorch. So Scorch is listening now to requests from the outside to start something. In this case, it is Slurm. So Slurm is feeding Scorch. So now it's started, everything is running, and it's waiting for requests. So now we run just on 2 nodes with srun. So we start a job with 2 nodes, run the DF application without gekkoFS. So in this case, we have just a temp directory, and now we would see 2 times 50 gigabyte that is available, or at least that is the size available is only 32, but you have 2 separate namespaces, and this is the file. Now we have a script here how to launch it with gekkoFS. Again, you need to set the config, then around here, and then you can just start it. So this will then be executed by srun in a couple of seconds. We of course use the new Slurm commands here to have also 2 ad hoc storage nodes that are shared with the application. And we run this DF shell script that we've just seen. So we see now that the storage system has been started. On the right, you see that Score did something, and then it was reported. And now the size that is available is 2 times because the namespaces are consolidated. You have the same capacity, this is represented here. The DF flow not directly to its path, but to the virtual mount point, which goes to the gekkoFS servers and then back. And this is how they work in Admire. And that's about it. Thank you.
Okay. Thank you very much. So we are stopping for a coffee until questions, maybe?
Yeah.
Questions.
Oh, yes.
Yeah.
Sorry. I forgot to ask if you have some questions for the speakers, people here online. Any question online?
I cannot see them. So.
People online can raise their hand and we can unmute
Yeah.
them.
Yeah, can you relay them because I cannot see them?
Yeah.
I'm trying to, but I can see no
Okay.
hand, so.
If you want to make any question to the people online, please raise the hand in your WebEx terminal, and we will open you the microphone.
All right.
So if we don't see any questions here in the room for the speaker? No? Okay, thank you, Mark.
Thank you.